Hello. In the last section, 2.6, we saw a list of basic functions, basic or parent functions. So now we're going to, this is a longer section on graphic techniques. So I'm going to do this into parts. So we can call this graphing techniques or transformations of graphs. Okay, so we're going to see several types of transformations. The first type of transformation, I'm not following the order of the book, but the first type of transformation is going to be translations or shifts. Okay, so where I'm going to use some of the basic functions that I covered in the last section. Okay, so I'm going to start working with the squaring function. So let's consider the function f of x equals x squared. I'm sure you remember the graph. Okay, so I'm going to draw the graph again. We use the point, the x value is -2, 0, 1, and 2. The y values are 4, 1, 0, 1, and 4. So that's a graph we did in the past. So that's why I'm not going through all the details. And this goes through, so the points on this function are -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. So we connect the dots. The graph is called a parabola. Okay, so that's a function we did. Okay, but now let g of x be f of x plus 4. So the input of f is no longer x is x plus 4. Okay, we're going to see what happens with the graph. When making the table, know that if x is -4, -4 plus 4 is going to be 0. And 0 squared is 0. So I'm going to take two values to the left and two values to the right. So let's take -3, -2, -5, and -6. So -3, if x is -3, -3 plus 4 is 1, 1 squared is 1. If x is -2, -2 plus 4 is 2, and 2 squared is 4. If x is -5, -5 plus 4 is -1, -1 squared is 1, and -6 plus 4 is -2, -2 squared is 4. So let's plot the points. Okay, so x values. And then y values are the same. The y values didn't change. Okay, so we got -6, 4, -5, 1, -4, 0, -3, 1, and 2, 4. So I'm trying to plot this. Sometimes this is challenging, but there it is. Okay, let's try to erase this little one. Okay, so if you observe the graph, it's the same as the graph of x squared, but it was shifted 4 units to the left. So I'm going to write a note that the graph of f of x or the graph of g of x defined as f of x plus 4 is the graph of f of x shifted 4 units to the left. And I'm going to do another transformation. Now let h of x be f of x minus 2. So that's going to be x minus 2 squared. If x is 2, y is going to be 0 because 2 minus 2 is 0 and 0 squared is 0. So I'm going to take 2 values to the left and 2 values to the right. Okay, so if x is 3, 3 minus 2 is 1, 1 squared is 1. No, that one is supposed to be 4. 4 minus 2 is 2, 2 squared is 4. 1 minus 2 squared is negative 1, or 1 minus 2 is negative 1. Negative 1 squared is 1, and 0 minus 2 is negative 2. Negative 2 squared is 4. And let's plot the points. Okay, so we got the points 0, 4, 1, 1, 2, 0, 3, 1, and 4, 4. So you compare this to the graph of x squared with the graph of the squaring function. It's the same graph, but it's shifted 2 units to the right. So we're going to write another note that the graph of h of x equals f of x minus 2 is the graph of f of x shifted or translated 2 units to the right. So here's the summary of horizontal translations. That's on page 268. So I'm going to copy that. I'm going to copy the summary. Okay, so given a function defined by g of x equals f of x minus c, where c is a real number, for every point x, y on the graph of f, there will be a corresponding point x plus cy on the graph of g. So the graph is going to shift c units to the right, so note that we have a negative sign. We have a negative sign there. So if c is positive, the graph will shift c units to the right, like the one we did. We have f of x minus 2. So minus 2, that means go to shift to the right. And the shift is going to be to the left if c is negative. So minus minus is plus. We have something like this: f of x plus 4. So we have plus, and the graph is going to shift 4 units to the left. So be careful with that. You're adding a number you're adding to a number to x, it's going to be a shift to the left. And if you subtract a number from x, the graph is going to shift to the right. Okay, the next type of translation is a vertical translation. So we're going to work with a different function. Consider now f of x, the absolute value of x. So that's another graph we did. We're using the points -2, -1, 0, 1, and 2. The absolute value of a negative number is going to be its opposite, and the absolute value of 0 or any positive number is going to be itself. We did this graph before. Okay, so we have the points -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. Okay, so we did the graph. We did the graph. But now this is what we're going to do. We're going to let g of x be f of x plus 2. So we are adding 2 to f of x. But f of x is the absolute value of x. So it's going to be the absolute value of x plus 2. So whenever we plot points, we're going to keep the same x values, but the y values are going to change. So we have the same x values. And then the y values, we're adding 2 to each y value. So 2 plus 2 is 4, 1 plus 2 is 3, 0 plus 2 is 2. 1 plus 2 is 3, and 2 plus 2 is 4. Okay, let's plot the points. We got -2, 4, -1, 3, 0, 2, 1, 3, and 2, 4. Okay, so now the graph, if we compare the two graphs, the graph of g is the graph of f, shifted 2 units upward. So the graph of g of x, defined as f of x plus 2, is the graph of f shifted 2 units upward. And one more example. Let g of x, or let h of x, be f of x minus 3. So now we're going to subtract 3 from each y value. So let's do that. The x values are not changing, the x values are the same. And we're subtracting 3 from each y value in the original function. So the y values of the absolute value functions are 0, 1, and 2. So 2 minus 3 is -1. 1 minus 3 is -2. 0 minus 3 is -3. 1 minus 3 is -2. And 2 minus 3 is -1. Okay, let's sketch the graph. Okay, so some points are -2, -1, -1, -2, 0, -3, 1, -2, 2, -3. And we can even include -3, 0, and 3, 0. So when plotting the points, let's see. You compare it to the original function, the absolute value of x, the graph was shifted 3 units downward. So the graph of h of x that's f of x minus 3 is the graph of f of x shifted 3 units downward. And here's the summary of vertical translations or vertical shifts. This is on page 267. Given a function g defined by g of x equals f of x plus c, where c is a real number, for every point x, y on the graph of f, there will be a corresponding point x, y plus c on the graph of g. The graph of g will be the same as the graph of f, but translated c units up if c is positive, and c units down if c is negative. Like in the example we did, we have f of x plus 2. So the graph is going to shift 2 units up. And f of x minus 3, the graph will shift 3 units down. Okay, so I'm going to do an example or 2 examples where we combine both type of translations. Vertical and horizontal. Okay, so we are going to use another basic function. We are going to use the graph of the square root of x to obtain the following graphs. The graph of the square root of x plus 2 minus 3, and the graph of the square root of x minus 3 plus 4. So again, be careful. because adding in horizontal translation, adding is a translation to the left, and subtracting involves a translation to the right. And with vertical translations, adding involves a translation up, and subtracting involves a translation downward. So let's do number 1. Our basic function is the square root of x. So there are going to be 2 translations or shifts. The graph of the square root is going to shift 2 units. We have a plus, so that's going to be 2 units to the left and 3 units down. Okay, so let's look at the graph. I'm going to start with the basic function. For this one, we only needed 3 points. The square root of 0 is 0, square root of 1 is 1, and square root of 4 is 2. Okay, so that's the graph of the square root function. Now the new function is the square root of x plus 2 minus 3. So I'm going to make another table for this one. The graph shifted 2 units to the left. So we're going to subtract 2 from every x value. 0 minus 2 is negative 2. 1 minus 2 is negative 1. And 4 minus 2 is 2. And we're going to add, so it's shifted 3 units downward. We're going to subtract 3 from every y value. 0 minus 3 is negative 3. 1 minus 3 is negative 2. And 2 minus 3 is negative 1. Yeah, I'm going to draw a separate graph. Okay. So we got negative 2, negative 3, negative 1, negative 2, and 2, negative 1. So that's the graph of g of x. So this one involved a vertical and a horizontal translation. And number 2, the function obtained from the square root function is the square root of x minus 3 plus 4. So the graph of the square root function is going to shift is going to be 3 units. We have the square root of x minus 3, so minus is going to be 3 units to the right. And 4 units, we have a plus 4, so that's going to be 4 units upward. Okay, so shifting 3 units to the right, that means we're going to add 3 to each x value of the square root function. 0 plus 3 is 3. 1 plus 3 is 4. And 4 plus 3 is 7. And we're going to add 4 to each y value in the square root function. 0 plus 4 is 4. 1 plus 4 is 5. And 2 plus 4 is 6. Okay, so x values. Okay, so we have y values from 0 to 6 and x values from 0 to 7. Okay, so we got what? We got the points 3, 4. So 3 units to the right, 4 units up. 4, 5, and 7, 6. So that ended up being the graph of h of x equals the absolute value of x minus 3 plus 4. Okay, so the first type of transformation was where translations or shifts. The next type of transformations is going to be reflections. Okay, so we now consider the absolute value function, and we're going to find, let's see. Yeah, we're going to use the opposite. We're going to find the opposite, or we're going to consider the function given by the opposite of f of x. Okay, so the absolute value function, actually I'm going to do a table with 3 columns. And we're going to compare the graphs. Okay, so we have for x, that's the absolute value function. Then we got the y values are 2, 1, 0, 1, and 2. The new function is the opposite of the absolute value function. That is going to be the opposite of 2 is negative 2, opposite of 1, opposite of 0 is itself. And finally, we're going to compare the graphs. Yeah, so let's draw the graphs. Okay, so the absolute value function passes through the points negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. This is the graph of the absolute value function. And g of x is the opposite of the absolute value function, so that goes through the points negative 2, negative 2, negative 1, negative 1, 0, 0, 1, negative 1, and 2, negative 2. So the important observation here is that, okay, start typing, that the graph of g of x defined as the opposite of f of x is the graph of f of x shifted or not shifted, reflected across the x-axis. So the graph was reflected in this sense, was reflected like this. So that was an example of a reflection across the x-axis. And the next one, we're now going to consider again the square root function. Okay, so we'll consider the square root function and the new function g of x is going to be f of the opposite of x, or the square root of the opposite of x. The first observation is that the domain of g has changed. The domain of g is no longer 0 to infinity, it's going to be negative infinity to 0, including the 0. Okay, so we are going to plot some points. So if I let x be 1, the square root of negative 1 is not going to be a real number. So we're going to take the opposite of 1. The opposite of, or the opposite of negative 1 is 1, and the square root of 1 is 1. And the opposite of negative 4 is going to be 4. The square root of 4 is 2. And I'm going to draw both in the same set of axes, the square root function and the function defined as the square root of the opposite of x. Okay, so first we have the square root function. And the other function passes through the points 0, 0, negative 1, 1, and negative 4, 2. Okay, so the function was reflected in this direction. So summarizing the graph of, did I call this G? Let me, well, I call this G again. That's fine. The graph of G of X defined as F of the opposite of X is the graph of F of X reflected across the y-axis. Okay, so summarizing the reflections across axes, those are on page 262. And I'm copying that. The graph of y equals the opposite of f of x is the same as the graph of f of x reflected across the x-axis. So if a point xy lies on the graph of f of x, then x comma the opposite of y lies on this reflection. And the graph of y equals f of the opposite of x is the same as the graph of f of x reflected across the y-axis. So if a point xy lies on the graph of f of x, then the opposite of x comma y lies on this reflection. So now that we know how reflections work, we're going to talk about symmetry. And that's going to be the last thing I'm going to do in this first part of the section. Okay, so that's on page 263. So I'm copying the I copied this box. The graph of an equation is symmetric with respect to the is symmetric with respect to the y-axis if the replacement of x with the opposite of x results in an equivalent equation. And the graph of an equation is symmetric with respect to the y-axis if the replacement of y with the opposite of y results in an equivalent equation. Okay, so this is what a graph would look like. Okay, so let's suppose you have some type of graph. So you can only say that if the graph is reflected across the x-axis, the graph is not going to change. Okay, so the graph of an equation is symmetric with respect to the y-axis. So this is symmetric with respect to the y-axis. Because if you reflect the graph across the y-axis, if you reflect it across the y-axis, the graph doesn't change. Or also, if the replacement of x with the opposite of x results in an equivalent equation. So if the point xy is on the graph, the point with coordinates the opposite of x and y is also on the graph. And on the other hand, a graph is going to be symmetric with respect to the x-axis. So I'm going to read this text again. The graph of an equation is symmetric with respect to the x-axis if the replacement of y with the opposite of y results in an equivalent equation. Okay, so let's say that this is the graph of an equation. If the point xy is on the graph, the point x, the opposite of y, is also on the graph. And then we have x, y, and the opposite of y. So this graph is symmetric with respect to the x-axis. Okay, so we're going to go over example 3. And this is going to be the last example I'm doing in this video. I'm going to finish it. I'm going to finish this material in the next video. So that's example 3. And we're on page 263. So test these equations for symmetry with respect to the x-axis and the y-axis. Remember, the graph of an equation is symmetric with respect to the y-axis if the replacement of x with the opposite of x results in an equivalent equation. So we're obviously going to do that without graphing the equation. Okay, in part A, the equation is y equals x squared plus 4. So we're going to test for symmetry with respect to the x-axis. To test for symmetry with respect to the x-axis, we're going to replace y with the opposite of y. If we get an equivalent equation, the graph is going to be symmetric with respect to the x-axis. Only problem is that we have that if I replace y with the opposite of y, I have that the opposite of y is x squared plus 4. Or y is the opposite of x squared minus 4. In any case, this is not equivalent to the original equation. So this is not symmetric with respect to the x-axis. Okay, so now let's test for symmetry with respect to the y-axis. We are going to replace x with the opposite of x. Okay, so y, replace x with the opposite of x. That's going to be the opposite of x squared plus 4. But the opposite of x raised to the second power is going to be again x squared. Okay, so we got that y is x squared plus 4, which is the same equation that we began with. That's the same equation. So this is symmetric. That's equivalent to the original equation. And the graph is symmetric with respect to the y-axis. Okay, so the first graph was symmetric with respect to the y-axis, but not the x-axis. Number 2, or part B, the graph is, we're going to test for symmetry. We're going to test the graph of x equals y squared minus 3 for symmetry with respect to the x-axis and the y-axis. Okay, so this is the equation. Okay, so we're going to test for symmetry. Let's start with the x-axis. We are going to replace y with the opposite of y. But the opposite of y raised to the second power is going to be y squared. So the equation looks we ended up with the same equation as the first one, as the original equation. So this is symmetric. The graph is symmetric with respect to the x-axis. The graph is symmetric. And let's test for symmetry with respect to the y-axis. So we're going to replace x with the opposite of x. And you can see now that the equations are not equivalent. Is that, or x is the opposite of y squared plus 3. In any case, the equations are not equivalent. So this is not equivalent to the original equation. And the graph is not symmetric, with respect to the y-axis. Third example. Part C, we have x squared plus y squared equals 16. If you remember the second section of this chapter, This is the graph of a circle centered at the origin with radius 4. So let's test for symmetry. With respect to the x-axis, we have x squared plus the opposite of y squared. But the opposite of y squared is going to be y squared. Okay, so we got the same equation, and with respect to the y-axis, the opposite of x is the opposite of x squared is going to be x squared. Okay, so in both cases we obtained the same equation. And the graph is symmetric with respect to both the x-axis and the y-axis. In part D, the equation is 2x plus y equals 4. So let's test for symmetry. With respect to the x-axis, we have 2x minus y equals 4. So that is not equivalent. To the original equation. And if we test for symmetry with respect to the y-axis, we have 2 times the opposite of x plus y equals 4, or the opposite of 2x plus y equals 4, which is also not equivalent to the original equation. So this is not symmetric with respect to any axis, to any of the axes. Okay, so we did symmetry with respect to axes, and the last topic on symmetry is symmetry with respect to the origin. That's on page 264. The graph of an equation is symmetric with respect to the origin if the replacement of both x with the opposite of x and y with the opposite of y at the same time results in an equivalent equation. So graphically, we could have something like, and actually we did one example of that. If part C, in the last example, is equivalent and is symmetric with respect to the origin. But there could be other cases, like something like this, like this looks kind of like the graph of the cube root function. So if xy is on the graph, the point with whose coordinates are the opposites of x and y, is also on the graph. Another one could be like the graph of 1 over x, which I'm going to cover in chapter 3. But this graph is going to have 2 branches, so I'm going to do this type of graph with more detail in chapter 3. And if the point xy is on the graph, the point whose coordinates are the opposite of x and the opposite of y is also on the graph. And I did one example. Parsing the last example was x squared plus y squared equals 16. We learned in section 2 of this chapter that the graph is a circle centered at the origin with radius 4. Okay, so when we did this example, we replaced x both, or if we replace both x and y with its opposites, we get that the opposite of x squared is going to be x squared, and the opposite of y squared is going to be y squared. So take any point on the circle. If xy is on the circle, then the opposite of x, comma, the opposite of y is also going to be on the circle or the graph. So finally, I'm just going to read some notes about symmetry, and that's going to be it. So a graph is symmetric with respect to a graph symmetric with respect to both the x and the y axis. It's automatically symmetric with respect to the origin. And then a graph symmetric with respect to the origin need not be symmetric with respect to either axis, like this one I did. Okay, so this example with the circle, the graph is symmetric with respect to both the x and the y axis. So it's symmetric with respect to the origin. But these other 2 graphs, they are symmetric with respect to the origin, and they are not symmetric with respect to the axis. Of the 3 types of symmetry, with respect to the x-axis, the y-axis, and the origin, a graph possessing any 2 types must also exhibit the 3rd type of symmetry. And a graph symmetric with respect to the x-axis does not represent a function. I'm going to stop here. Thank you for listening.